we are going to look at simplifying radicals. Radicals are things like square roots and cube roots. So what happens is that you need to break it down to its factors, okay, or its prime numbers. And then whatever the index is, so remember when we're writing a radical, that this is the index. Okay, that's letting us know what it is, what kind of root it is. Okay. Now, if it's a square root, we just don't put anything there. So on example A, when it has root 75, that's the same thing as the square root of 75. What happens is mathematicians are lazy in their writing, so since square root is the one that we use most frequently, we just drop the 2. Okay? So if you are unfamiliar with your perfect square numbers, now might be a good time to re-look at them. So if we look at 1 squared, that's 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and that's probably, well, I guess 15 squared is probably useful to know as well. 225. Okay? What you're trying to do is break down the numbers and find the greatest perfect square that it has. So here, notice there are a couple of rules that will help you break it down. So if a number is divisible by 2, it ends in 0, 2, 4, 6, or 8. If a number is divisible by 3, if I add the digits, so like on this one, if I do 7 plus 5, that would give us 12. If your sum is divisible by 3, then the whole thing is divisible by 3. So then I know that this is divisible by 3. That trick also works for 6 and 9. So not for 6, just for 9. If it's divisible by 6, you have to check for divisible by 3 and divisible by 2. If it's divisible by 4, the last 2 numbers are divisible by 4. If it's divisible by 8, the last 3 numbers are divisible by 8. So those are some rules to help you remember. So here, I could break it down to 3, right? And then if we want to see how many times 3 goes into 75, then I get 25, and then I get 5 and 5. Or if you had thought, well, 5 goes into this, if you think 5 goes into it, then you get 5 and 15. Well, 15 is 3 and 5. So notice either way I break it down, I've got 2 5s and a 3. Right? So since it's a square root, you want to pick groups of 2 since it's a square root. Right? Now, if you want to look at how we could rewrite this, I could also rewrite this as, I did something that I don't actually want to do. There we go. 3 and 5. I could actually write this as the square root of 3 times 5 times 5, which is really the same thing as 3 times 5 squared. Now, if you remember about multiplying polynomials, this is the same thing as the square root of 3 times 5 squared. Well, 5 squared, square rooted, the squared and the root undo each other, so then this would just be 5 times by the square root of 3, right? So this is essentially what we're doing. We're finding pairs so that we can use this idea here that the square root of a number squared is just the number. Right? So if you find a pair, what happens is that the pair comes out of the root, and then the non-pairs stay underneath and they get multiplied. So this would turn into 5 root 3. So it's kind of like dating. So when you're dating somebody, you want to find somebody that has similar interests. So in the math world of dating, they have to be the exact same number. So you have to find somebody that's exactly the same as you. So in this case, 5 is the same as 5. And when you go out on a date, not right out because that's not good for the coronavirus, but when you go out on a date, you go out of the house or out of the radical, outs to go on your date. So they are underneath the radical, so they go out of the radical. And when we talk about dating, it takes two people to go out on one date. So these two people are just out on one date, so there's only 1 5 that comes out. That helps you remember great. If not, it's fine as well. So here, if we look at 24, we want to think of, is there any square number? The reason I went over the square numbers for 25, or for A, so I know that 25 goes into 75, so then I know the square root of 25 is 5, right? So then I'm just looking at this part. Well, the square root of 25 is 5, so then I end up getting 5 root 3. So it's often nice if you can come up with a perfect square number that's in there. If there's not a perfect square number that's in there, then you can just break it down to your primes and find any pairs. So for example, for 24, there's a lot of different ways that you could break it down, like you could do 8 and 3. But notice I've got a 4, right? That's a perfect square that goes into it. So if I continue to break this down, I have a pair of 2's. This 2 doesn't have a pair. This 3 doesn't have a pair. So this 2 comes out of the radical. This 2 has to stay under the radical, and this 3 has to stay underneath the radical. So then you multiply on the outside, anybody that went out on dates, and then you multiply underneath. So this gives you 2 root 6. Now, if you hadn't picked 4 and 6, say you had done 8 and 3, you'd end up with the same numbers. You would just get there in a slightly different way. Okay. Now, what happens when there's a number out in front of it? Well, we proceed on just like we would normally do. So this is 40. So if I think about my perfect squares, I know that 4 goes into it, and then I have 10. So another way you could think of this is that this is 3 times the square root of 4 times by the square root of 10. Well, we know that the square root of 4 is 2, and then the square root of 10, notice that's just 2 and 5. There's nobody that can go out on a date here, so I can't do anything, so then I'm just all done. So this would give us 6 root 10 when I multiply the things outside. Now here, the important part, the 3 outside was already on a date. So it continues to just say outside the radical, and then anything that comes outside the radical, notice that you're multiplying on the outside. Now, if I didn't do it this way and I just continued breaking it down, so for example, if we did, we just had it as 3 square root 40, and I broke 40 down to 4 and 10. This is 2 and 5. This is 2 and 2. So notice this is a pair of 2's that can go out on a date. Notice the 3 is its own date that already was out, that you're maybe meeting up with, like at prom, you go on lots of dates. And then 2 and 5 don't have dates, so they have to stay at home. Right? So these stay at home, and we've got the 3 that stays out on their date, and then the 2's join them, and we multiply the outsides, and we multiply the underneath, so we end up with 6 root 10. Okay? So it's advantageous to know your perfect squares to kind of help you break down your number and see how to get those perfect squares so that you can undo the root. If we take a look at another example, now what happens when it's a little bit different, like with a cube root? Well, instead of thinking we go out on dates in groups of 2, on this one we do groups of 3 because the index is 3. So if I have the cube root of 54, now you could look at your cubes, your like 1 cubed, 2 cubed, 3 cubed, 4 cubed, and so on and so forth. I'm just going to break down my numbers. So I know that 9 times 6 is 54. 9 is 3 and 3, 6 is 3 and 2. So notice here we have a group of 3. So the 3's, I need 3 of them to come out because that was our index number. So the 3's go out on a date. We keep this, notice I keep the index of the 3 in the root, like in the little V part of the root. And then underneath, we still have the 2 that stays under and didn't go out on the date. So this would be 3 cube root of 2. Okay? So it's very similar to what we have done before, except for we have, we have 3 that come out instead. Now, what happens when you have variables is the word that I wanted. Goodness. Okay. If we look here, so if we take this, we can look at it piece by piece. So for example, if I take the cube root of 8 times by the cube root of x to the 5th. Well, if we take a look at the cube root of 8, notice if I break down 8, that's 4 and 2 and 2 and 2. So notice I've got a group of 3 2's, so those will come out. Now, if there's nothing left under the root, this part of the root disappears, right? So there it would just be the 2 on the outside. Now, if we look at x to the 5th, I need to make this look more like an exponent. Okay, so goodness gracious. Cube root of x to the 5th. If we think of x to the 5th, well, that's really x times x times x times x times x, right? So if I look here, I have a group of 3 that can come out on a date, and then I've got 2 loners that can't go out on a date. So these x's join the 2 out of the date, but these x's right here, they cannot join because they don't have a third one to go out with them. So then this turns into 2x cube root of x squared. Notice underneath I multiplied the variable. Okay. It's conventional to do the number, then the variable, then the root, and then the number and the variable. Okay. Now there ends up being a shortcut with this, because what happens is we're looking here, how many groups of 3 do we have? So when we're looking at groups of 3, that's really dividing. So I'm doing 5 divided by 3. Well, that gives us 1, and we have a remainder of 2. So notice that the 1 went with the exponent that was on the outside, right? And then our 2 went with the exponent that was underneath. Now you can't see those numbers very well. Okay. So what happens is, however, whatever your answer is, that's the exponent on the variable on the outside of the root, and then whatever your remainder is the variable or the exponent with the variable underneath. So if we do that pattern on the next one, okay, so here we're thinking 8 divided by 3, well 3 goes into that twice and we have a remainder of 2. If we do 6 divided by 3, that gives us 2, remainder nothing. So that means that here we're going to have an x to the second, and then we're going to have a y to the second from here, and then we have the cube root of x to the second, and then y to the nothing. But we don't actually have to show the y to the nothing, so we can just do x squared, y squared, cube root of x squared. Remember that anything to the 0 power is 1, so then if we think, well, x squared times 1, well, that's just x squared. So that's why we can simplify it to this. So that's how you simplify your radicals.